that tells us the number of ions that are produced. So we use 250 kVp X-rays as our standard. So basically we use an electromagnetic radiation. We give it 250 kVp. We know that 1 Roentgen is equal to 1 rad. Okay, remember we said that a rad is 100 ergs per gram. And a Roentgen produces anywhere between 87 and 97 ergs per gram. That's why they just kind of made the two the same. But basically, the standard that we compared the other radiations to is a 250 kVp X-ray beam. So the first thing we do is we expose the water. Let's say we expose it to 1 rad of 250 kVp. We measure the number of ions, and let's say that we get 1,000. So 1,000 ions to 1 rad. And this is just hypothetical. Okay, but a 250 kVp X-ray beam is the standard. Okay, so we get 1,000 ions with that. Then the next thing I do is I expose this to a source of neutrons. And the neutrons, we give it 1 rad of neutrons. So basically we give it the same dose, only this time with 1 rad of neutrons, instead of getting 1,000 ions, I get 10,000 ions. So basically what that's telling us is that for the same amount of absorbed dose, I'm producing 10 times more ions. So therefore the quality factor is going to be 10. Because basically the dose of unknown radiation, or the number of ions produced with the unknown, divided by the dose for the standard. So we get a quality factor of 10. So for the same amount of absorbed energy, it produces 10 times more damage, is another way of putting it. I don't know why this thing, let me just see if I can change this thing for a minute. You know, it's kind of an interesting effect, I don't.
It looks kind of dizzy, though.
But anyway, so what we've come up with, the quality factor for like alpha particles is 20, neutrons is 10, beta particles, beta because they're like an electron, they have a range of between 1 to 1.6, gamma rays and X-rays. They have a quality factor of 1. Okay. The relative biological effectiveness, on the other hand, this is where we actually take tissue and we expose the tissue to radiation to see how much it takes to produce an effect. Well, these are some other terms that you should be aware of here. LET, okay. The amount of ionization that occurs or the amount of damage that occurs is based on this concept here of linear energy transfer. And notice it's the amount of energy deposited by the length of travel of the radiation. The unit that we use to express it is keV per micrometer. This tells you how much energy is deposited per micrometer.
Sorry, the LET is the amount of what?
Oh, it's the amount of ionization that occurs along the path of the radiation through the body.
Thank you.
Okay. And it's actually a combination. Okay, the first thing is what they call the specific ionization. So, for example, specific ionization is the number of ion pairs per micrometer. Okay, so if this is my source of radiation, and I measure the path of ionization along here, let's say that we get 100,000 ion pairs. Okay, so this is a 1 micrometer distance here. So remember, it's a millionth of an inch. Okay, that's a lot of energy being deposited along that. Okay, so we have the number of ions. What we're looking at here, this is the specific ionization. Okay, now to calculate the energy that was actually deposited, if you look down here a little bit further, the average energy needed to produce an ion pair in human tissue is 34 electron volts per ion pair. So if I take my specific ionization and multiply that times the average energy to produce the ion pair, by multiplying those two together, this is what our answer would be. Okay, so we had 100,000 ions per micrometer, and we had 34 electron volts per ion pair. So basically 100,000 times 34 electron volts. This means that we deposited 3.4 MeV per micrometer. So this is what the LET would be. So obviously the more energy that you deposit, the more damage it's going to do. Okay. The relative biological effectiveness, or what we call the RBE. Okay, again, normally what we do is we take samples of tissue. Let's say, for example, we have liver tissue. We expose this group of liver tissue to the 250 kVp X-ray, and we find that it takes 1,000 rads to kill all the cells. So we have all these little happy cells in here. We expose them to radiation and kill them. Okay. Then over here, I take my unknown radiation source, and let's say that in order to produce the same effect of killing all of the cells over here, it only requires 50 rads. Now, when we're talking about effects, we could be talking about things of DNA changes. Cells have been exposed to radiation, it affects their ability to divide. Normally your cells will divide at predefined times. So like every hour your bone cell divides. Usually when you expose a cell to radiation, that changes its rate of division. So usually for maybe a generation or two you'll have cells that are having a problem. But then they'll go back to normal after that. But okay, so with this group over here, okay, it took 50 rads to kill all the cells. And let's say that I find out that this is an alpha emitter. So to calculate the RBE, it's going to be on the dose of our standard. So 1,000 rads to kill, that's the standard dose, divided by the rads to produce the same effect of our unknown radiation. In this case, it's the alpha particle. So the RBE for this is going to be 20. So in other words, alpha particles are 20 times more damaging when compared to the X-rays. Okay, does that make sense? One of the things that we're using, you've heard that we talk about RADs and RAM and things like that. You're going to hear the term dose equivalent. Dose equivalent is the RAM, but we also have now what we call effective dose equivalent. Have you heard that? Okay, effective dose equivalent I feel like a magician here.
It's starting to hurt the ice.
Yeah, it's
Is it?
getting dizzy.
Is it?
Yeah.
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 Let me turn this.
Watch it.
Let me see if I can. Let me turn this off and on and see if that does anything.